So today we will be going over stoichiometry, as well as finding out limiting reactants to certain equations that we'll be working with, and working with a certain amount of moles, and then converting it to what it will be produced, and what is going to, like I said, what is going to be the limiting reactant. So we're going to be going over chapter 4 problems again, just as last week, but we're going to be going over stoichiometry and limiting reactants mainly. So we're going to start with question 44D. And 44D asks us to write the balanced equation, then outline the steps necessary to determine the information requested in each of the following. So we have the number of moles and the mass of water formed by the combustion of 20 kilograms of acetylene, I believe that's how you pronounce it, C2H2, and an excess of oxygen. So when we're working with a combustion reaction, what's always going to happen is we're going to start with, our polyatomic ion here, or acetylene, C2H2, and because it's in a combustion reaction, we're going to be combining with oxygen gas, and that's going to be on the left side of the equation. And that's always going to form water and CO2, because that's how a combustion reaction works. So we have H2O here, and we have CO2. But this is not balanced yet, so we have to identify what atoms we have on the left and the right, and make sure we have an equal amount on the left and the right, and then we can balance those. So we have carbon, and we have hydrogen, and we have oxygen on the left and the right. So those are our atom species. And it looks like on the right we only have one, and we have 3 on the right, and we have 2 on the right. And then on the left we have 2 carbons, we have 2 hydrogens, and 2 oxygen. So because we have a different amount of oxygen as well as carbon, we're going to target those. So we will put a 2 on the hydrogen here, so that we have, 2 on the CO2. So since we put a 2 on the CO2, that'll change the amount of coefficients. So now we have 2 carbon, and we have 4 oxygen. We actually have 5, my bad. We have 5 here. And so because we have 5 here and 2 on the right, we're going to have to put a different amount of oxygen on the left. So that'll have to be, let's see here. But since we have an odd amount of oxygen on the right, we're going to have to put a different number of coefficients on the right so that it has an even amount, if that makes sense. So because we have 2 here, we're going to have multiples of 2, and then we have 1 oxygen and then multiples of 2 here. So whatever we do right now, it's going to be odd, but we're going to have to add it so that it's an even amount, so that we can multiply the oxygen here to also be an even amount, because that only can be even. So to get that to happen, we're going to have to put also a 4 here. And then we're going to have to put a 2 in front of the H2O. And so let's rearrange how much we have, and I'll explain why we did that. So we have now 4, and we have 2 of the oxygen, and so that will make this have an even amount, so that we can have an even amount on the left side as well, because like I said, there's multiples of 2, so we're gonna have to have an even amount of oxygen on the right, so we can balance the left. So that'll be 4 hydrogen on the right, and then we have 4 times 2 is 8, and then 8 plus the 2 that's distributed to the oxygen here. We now have 10 oxygen, and we have 4 carbon. And so because we had the 2 waters and the 4 carbon dioxides, we're going to have to balance the left side now. So now that we have 4 carbons, now we're going to have to put a 2 in front of the acetylene. So that will make it so that we have 4 carbon, 4 hydrogen, and now all we have to do is just balance the oxygen gas here, because that is the only thing that is unbalanced, and because we have 10 on the right, now we have an even amount, and we'll just need to put a 5 in front of the oxygen gas here, and so then that'll make it have 10. So now this equation is fully balanced. We can get to answering the question now that we know the number of moles of everything in this reaction. So it's asking for the number of moles and the mass of water formed by the combustion of 20 kilograms. So we're going to start with the mass because that's what we have. So we have 20 kilograms of the C2H2. And so we're going to want to get to water. So it's asking for the moles and also the grams. So we're starting with kilograms here, so we want to get that to grams. So in 1 kilogram, there's 1,000 grams, just so that we have even units all the way across. And so now we want to go from grams of acetylene to moles of acetylene, and so that requires a molar mass. So let's calculate the molar mass. So the molar mass of C2H2, let's write this down here. Of C2H2 equals, so there's 2 carbons, so 2 times 12.011, because that's the molar mass of carbon, and then we have 2 hydrogens, and so it's 2 times 1.008 for the hydrogen molar mass, because we have 2 of the hydrogens and we have 2 of the carbon. So adding that all together, I did the math earlier, so it's quicker to get to, so it's 26.038 grams per mole. And so now that we have the molar mass of C2H2, we can plug that in and then convert it to moles of C2H2. So we have grams on top, so let's put the grams on the bottom. So we have 26.038 grams per 1 mole of C2H2. And now we're in moles of C2H2, but we want to get to moles of water. So that's when we use our reaction that we have. And so since we have 2 moles of the C2H2 and we want to get to the moles of the water, for every 2 moles of the C2H2, 2 moles of water are also produced. So we're going to put the 2 moles of C2H2, because we're still working with moles of C2H2 on the top, so it cancels out. And then we want to go to 2 moles of H2O. So that'll give us, I'm going to move this to the left, that'll give us the moles of water. So that's what it's asking in this problem. And so since it's asking for, or it gave us 20.0 kilograms, that is 3 significant figures, because the 0 is after the decimal place and there's values before it. So we have 3 significant figures, so our answer will be 3 significant figures. So that'll give us 768 moles of H2O. And so it not only asked us for the number of moles of H2O, but also the mass. So that's just a simple conversion using a molar mass of H2O to get from moles to grams. So we're going to calculate the molar mass of H2O. So let's write that down right here. So the molar mass of H2O, we have 2 oxygens, 1 oxygen, so 1 times 15.999, and we have 2 hydrogens, so 2 times 1.008, and then when we add those up, we will get a value of 18.15 grams per mole. So we're going to use this molar mass that we just calculated, and we're going to take the amount of moles of H2O and bring it right over here. And then we're going to use that molar mass conversion. So we have moles of H2O, so we want moles on the bottom to cancel it out. So for every 1 mole of H2O, or water, we have 18.015 grams of H2O. So multiplying that out, we will get a value of 138, or 13837.46832, and that's grams. And because this is such a large number, most of the time you'll want to simplify it down to a number that is easier to read and more consistent with what it started with. So if it gave you kilograms in the beginning, it's just common sense to also put it in kilograms. So it's because this is such a large number, we want to simplify it down. And then put that smaller or that larger amount in the unit, because kilograms, it's, a large amount of grams, so the kilo is still there, but in the unit. So that number is also equal to 13.8 kilograms, just dividing by 1,000. And since we have 3 significant figures, we started with 20.0, our answer is going to be in 3 significant figures as well. So that is our answer. It produces 768 moles of H2O, and it also produces 13.8 kilograms of H2O. Okay, so let's move on to the next question. Let me know if I'm going too fast. I can always slow down or go over anything else. But yeah, let's go over 47. So this problem states gallium chloride is formed by the reaction of 2.6 liters of a 1.44 molarity, that's what the capital M is, solution of HCl or hydrochloric acid. According to the following equation, 2 gallium plus 6 hydrochloric acids equals 2 gallium chlorides plus hydrogen gas. Outline the steps necessary to determine the number of moles and mass of gallium chloride. Okay, so we have a few values here, and it says that we need to find the number of moles and mass of gallium chloride. So it's similar to the last problem that we worked with when we found the number of moles that water is produced, and also the mass of water that is produced from the reaction. But instead, we're working with a different compound, gallium chloride. But this time it already gives us the balanced reaction, so that makes it a little bit more simple to start with. So what we're going to do is whenever it gives us the amount of something that we have, usually that's a good place to start. So we have a certain amount of something. So we're going to start with the amount of liters of gallium chloride that we have. Or sorry, we have 2.6 liters of HCl. So we have 2.6 liters of HCl. So we're going to start with liters of HCl. And then we want to use that molarity to figure out how many moles we have in that in the amount of stuff that we have of the HCl. So we're going to multiply that by the HCl molarity, and then that will get us moles of HCl. And then what we want to do then is, since we have HCl on the left, but then we have gallium chloride on the right, we're going to look at the mole ratio to then convert, okay, for every 6 moles of HCl, we're going to get 2 moles of gallium chloride. So that's going to be our next conversion. So we're going to use the moles of gallium chloride. So mole ratio to gallium chloride. So that will get us moles of gallium chloride. So that's our first, that's one of our first answers because it asks us for the number of moles. And then after that step, then we want to find the mass of gallium chloride. So then we're going to want to use the molar mass to get it from moles to grams. So once you multiply by the molar mass of GaCl3, then that will produce grams of GaCl3. So those are the two answers that it asks, moles of gallium chloride and grams as well. So we're going to actually write that out and perform the calculation. So we had 2.6 liters of HCl to begin with. And just as our step before, we're going to use the molarity of the HCl to then get to moles of HCl. So for every 1 liter of the solution, we're going to have 1.44 moles of HCl. Yep. And then we're in moles of HCl, and then we're going to use the mole ratio to gallium chloride. So for every, what is it? Yeah, it's 6 moles of HCl, 2 moles of gallium chloride is produced. And now that we're in moles, we can multiply that out, and that's going to be our first answer. And that's going to be 1.248 moles of gallium chloride. And so now that we have moles of the gallium chloride, we can also use the molar mass of it. And the molar mass, I'll just write down here, molar mass of gallium chloride, it's multiplied out. So we have 3 chlorine, so 3 times 35.453. And then we have 1 gallium plus 1 of the gallium, so that's 69.723. And then adding that all together, we will have a molar mass of 176.002 grams per mole. So that's the molar mass of gallium chloride. So since we have the moles of gallium chloride right there, we're going to use that again. And let's just say this question just asked for the mass of gallium chloride. You can simply put the next conversion right here. But since it's asking for moles and then also grams, I'm breaking up the conversions, but you can go ahead and go straight to the mass if that's what it's asking for, whichever way is easiest for you. Yeah, so we're going to start with the moles, so that's 1.248 moles of gallium chloride. And for every 1 mole of gallium chloride, sorry, it's getting a bit cramped here. For every 1 mole, we have 176.002 grams of gallium chloride. And so that will give us an answer of 219.8 grams of gallium chloride. Awesome. So those are our 2 answers. We have moles and we have grams. So that is how we solve that problem and figure out how much we have of something given the following reaction. So let's move on to 57. So 57 asks us of what volume of a 0.2089 molarity of potassium iodide solution contains enough Ki to react exactly with copper, I believe that is nitrate, in 43.88 milliliters of a 0.3842 molarity solution of copper nitrate. So we have the given equation again, so we don't have to solve or balance anything, which is nice. So just as before, it gave us molarities, so that's going to be used later on, but we're also given, so we're given a initial amount of something, so we're going to start with that. So we have 43.88 milliliters of the copper nitrate, so we're going to start with that. And then in the end, we want to find the amount of liters of the Ki that we need to produce that amount. So we have 43.88 milliliters, and we need to convert that to liters because molarity is in liters, not milliliters. So for every 1,000 milliliters, there is 1 liter. And now that we're in liters, we want to get to moles of the copper nitrate. Because we want to figure out how much we actually have in moles, and then we can use a mole ratio, and that's how we can. And then once we have the mole ratio, similar to last time, it's asking for a volume, so that's an indicator that we're going to need a liter amount. And it gave us 2 molarities in the equation or in the question, so we can use the second molarity of the Ki to then get to liters. So I'll show you what that looks like in the conversions. So we have 1 liter, and this is of the copper, NO3. So we are in liters of that, so we're going to put liters on the bottom, and we're going to use the molarity that it gave us in the problem. So we have 0.3842 moles of copper, NO3, 2. And now that we're in moles of the copper, compound, we're going to want to get to moles of the Ki. So we're going to do a mole ratio conversion. So for every 2 moles of the copper NO3, we have also 4 moles of the Ki. So that is our ratio. So we're going to put 2 moles of CuNO3 on the bottom here. And we have 4 moles of Ki. So now that we're in moles of Ki, when we want to get to liters of Ki, and so then that's when we will use the molarity of Ki that it gives us right in the very beginning. So for every 1 liter, we have 0.2089 moles of Ki for every 1 liter of Ki. So now we are in liters of Ki, and so that all comes to an amount. And since we have, in the question, it gave us 4 different values, and they all have 4 significant figures. So your answer is going to be in 4 significant figures. So we have 0.1614 liters of Ki. And I calculated that out earlier. So that is the answer to 57. As you can see, there's a pattern going on. You always start with what you have, and then you always use, oh yeah, let me answer your question. So you went from volume to moles, and now you're trying to find the molarity of Ki to know if there is enough. So this, there already is enough. So let me try to phrase it a different way. So we want to start out with the volume that we're given of something. So we know it says to react exactly with copper, NO3. So we need to start with that solution, that amount first. And then we need to figure out in that solution how many moles we have of that. So then since we have, the amount of stuff, and then we figure out the moles of how much is in that using the molarity, then you convert that into Ki. Because then you use the ratio of how much CuNO3 needs to react with Ki to produce this whole right side of the equation. So you have to figure out what's the ratio. So for 2 of this, we need 4 of this. And so using that ratio, then you can get to the amount of liters of Ki. So in the previous problems, it was asking us to figure out how many moles of it. We're just finding the amount of liters of it, so it's the same kind of process. So that's why we use the molarity of Ki at the very end, because then we can actually figure out how many liters are produced. So we're not figuring out the molarity of Ki, like you asked in your question, because it already gave us the molarity. We're just figuring out how many actually liters that we have. Does that answer your question? Yeah, of course. Yeah, I can move. Okay, awesome. Yeah, it sometimes, in each of these questions, it's changed just slightly, and so it's hard to kind of wrap your head around what it's actually asking for. So what always helps me is, since I'm used to solving these problems, so before, when I wasn't as used to it, what I would do is I would write down everything that I have. So for this previous question, what helps is writing down all of the values that it gives us in the problem, and then writing down what it's asking you. That is where I find the most trouble, is trying to visualize the question. Yeah, for sure. Yeah. Yeah, so visualizing the question for sure, this would help. So I write down, okay, in the problem it says what volume. So what volume of Ki contains enough to react? So it's asking for the volume, and so volume is in liters. So volume of Ki is unknown, right? That's what we're asking. And so then it gives us the molarity of Ki, and then it also gives us the amount of the CuNO3. And then it also gives us the molarity of the CuNO3. 8, 4, 2. So this is what we already know, and then using that we can figure out what the question is asking, and that's the amount of liters. So since like you were a bit confused on like, oh, are we trying to figure out the molarity of Ki? No, we already have that. So it already gave us in the question. So if that helps at all, it can benefit you to write down what we have and what we are trying to figure out. To try to visualize it. Okay. Yeah, hopefully that helped more. So let's move on to another question. And so this is asking for limiting reactants. So it's asking, what is the limiting reactant in a reaction that produces sodium chloride from 8 grams of sodium and 8 grams of diatomic chlorine? Okay, so it does not give us a reaction here, so we will have to write that and balance that before moving forward. So it's asking for a reaction that produces sodium chloride. So it produces sodium chloride, so that's going to be on the right side. And sodium chloride, we have Na, and sodium is a 1 plus charge, and chlorine is a 1 minus charge, so that's going to be a 1-to-1 atom ratio of sodium chloride. So we have sodium chloride on the right, and it says that produces from sodium and diatomic chlorine. Okay, so diatomic chlorine is in the form of a gas, and then sodium is an ion. So let's write that down on the left. So we have Na plus on the left, and we also have diatomic chlorine. So that's diatomic, di is 2, so we have 2, and that's a gas. And this is a solid because it's a salt, and this is an ion. Or it could be solid. I'm not sure in this problem, but it doesn't really ask you for the states right now, so I wouldn't worry about it. Yeah, so we can see that we only have 2 different atoms, and so we have sodium and we have chlorine, and sodium and chlorine. And on the right side we only have 1 of each, and on the left side we have 2 chlorine and 1 sodium. So if we put a 2 in the front of the sodium chloride, that'll change us to 2 of each, but now we don't have enough sodium on the left, so all we have to do is put a 2 here, and then this reaction is balanced. So we have 2 sodium ions, 1 compound of the diatomic chlorine, and then it produces 2 sodium chlorine compounds. So it's asking for the limiting reactant. And it also gives us, so I'll write that down. So what is the limiting reactant? And a limiting reactant, what it means, just to clarify, it's basically the thing, I mean, it is in its name, the limiting reactant, but it's the thing that really is the main factor to how much something is produced. So if one of them produces a lot, so the reactant then produces a lot on the right side of the equation, and then another reactant produces not very much, we know that the one that doesn't produce very much, that's the limiter, because if we have an equal amount of both, if one is going to produce less on that rate, then that is what is limiting the reaction. So that's what is the limiting reactant. So we're going to calculate that. I'll show you what that looks like. So it says that we have 8 grams of sodium and 8 grams of Cl2. So given that information, we are going to see how many moles of the sodium chloride is produced from what we have. So we have 8 grams, let's write this down, 8 grams of Na. And since we're starting with grams, we need to use the molar mass to get to moles. and the molar mass of sodium is 22.990 grams of sodium, and we have 1 mole of sodium because it's a molar mass, so that's grams to moles. And now that we're in moles of sodium, we can use the molar or the mole ratio from how much we have of sodium and how much it produces of the sodium chloride. So in our reaction we have 2 here and we have 2 here. So our mole ratio is just 2 to 2, 1 to 1. Yeah, so we're going to start with 2 moles down here to cancel it out. So 2 moles of sodium, and then that's going to give us 2 moles of sodium chloride. And calculating that out, we will have a 0.348 moles of NaCl. So that is how much the sodium ion is going to produce of the sodium chloride. So for 8 grams of sodium, it's going to produce 0.348 moles of sodium chloride. So we're going to compare that same process, but for the diatomic chlorine, and see how much it makes of the sodium chloride. And then based on that, we can see which amount is the least, and then that will be the limiting reactant. So from the problem, we also have 8 grams. So 8 grams of Cl2, and the molar mass of that is just 2 times the chlorine atoms, so that's going to give us 70.906 grams of Cl2 for every 1 mole of Cl2. And so ratio again, we have 1 Cl2 for every 2 sodium chlorides. So that's different than the last mole ratio. So for every 1 mole of Cl2, we have 2 moles of sodium chloride. And so multiplying that out, we will get a value of 0.226 moles of sodium chloride. So if you can see, the sodium produced 0.348 moles, but the diatomic chlorine, it produced 0.226 moles of sodium chloride. You had a question? How do you know to put sodium chloride on top? Sodium chloride on top. Yes, okay. So let's break down these conversions a little bit more. So we started with how much we have, right? We have sodium or we have chlorine. And so since we're working with grams of both, we want to get to moles. So that's when we use the molar mass ratio. And so now that we're in moles of sodium, we want it, our end goal is to find out how much is produced of the sodium chloride. And so that's how we know to put it on the top, because we're going from moles of sodium and using that ratio to moles of sodium chloride, because we put it on top because that's what we're finding. And so it doesn't go on the bottom, because if we put, let me just erase that so it's not very messy. Like right here, we have moles of sodium. If we put moles of, cancel Na out. Yeah, so we want to, our units in the end need to be moles of sodium chloride. So the red highlight that I have here, we need to make sure that we don't have any units of just sodium, and so we're going to use that ratio to cancel Na out. It's just to not have sodium in our units, because we want sodium chloride as our units. So that's why we go from grams of the chlorine gas and then cancel it out. Just we don't have the chlorine gas units anymore. And now we're in units of moles, right? And then moles of chlorine gas, cancel that with moles of chlorine gas, and then we're left with the units of sodium chloride. So just canceling out means we don't have the units of it anymore. Does that answer your question? Okay, yeah, sure. Awesome. So let's move on to the next one. So I believe the next one, that's the last question that we have for today. Yeah. So it asks us, in a laboratory experiment, the reaction of 3 moles of H2 with 2 moles of I2 produced 1 mole of HI. Determine the theoretical yield in grams and the percent yield for this reaction. So this does not give us a reaction to start with, so we're going to have to write it ourselves, but that is no problem because we are chemistry masters. So let's start with what we have on the left side of the reaction. So we have H2 and we have I2, and it produces HI. So on the left side we're going to have H2, so that's H2 gas, hydrogen gas, and then iodine gas, and then it produces HI. And I believe, yeah, HI. Okay, so on the left and the right we have atoms of H, hydrogen, and I, iodine. So let's make sure we balance that out. So on the left we have 2 of each because they're diatomic ions, and on the right we have 1 of each, and so all that we have to do is just put a 2 in front of the HI, and now we have 2 of both, and so everything checks out. So this is balanced. Okay, so let's get on to what the problem is asking us. So we have a reaction of 2 different things, right? We have 2 different amounts of the hydrogen gas and the iodine gas, and it produces a certain amount of the HI. So what it actually theoretically is going to produce is going to be different than what is actually going to be produced. So I'll show you what that looks like. So we're going to start with what we have. So we know that we have 3 moles H2 and we have 2 moles of I2. And so we want to know how many moles are produced of the iodine. Sorry, HI, not iodine. But it doesn't just ask for the moles of HI, it asks for the theoretical yield in grams. And so after we go from moles to moles, so moles of H2 to moles of HI, we'll need to use a molar mass to then get to grams. Let's write that down. And then molar mass will get us to grams of HI. So that is our process. We're going to start with what we have, and it's asking what is produced in HI in terms of grams, and so we use a molar mass to get there. So let's get started. We have 3 moles of H2, and we're going to use a mole ratio. So in our reaction here, we have 1 mole of H2 to 2 moles of HI. So we're going to put that on the bottom here to get rid of those units. So we have 1 mole of H2 for every 2 mole of HI. And so now that we're in units of HI, mole HI, we want to use the molar mass, like I said. So for every 1 mole of HI, so that gets rid of those units, we will put the amount of grams on top of the molar mass. So for HI, the molar mass is 127.912 grams of HI. And so that will give us the amount of grams that is going to be produced from the hydrogen. And so now we're going to, I'll write down the answer in a second, but what we're trying to do here is we're going to figure out what is the limiting reactant. So we're given a certain amount of moles of hydrogen, a certain amount of moles of the iodine, and they're both producing HI, but we have to figure out what is actually going to be produced. So we're finding the limiting reactant, and then that is going to be the theoretical amount that were produced, and then we're going to figure out the actual percent yield, because it tells us that we actually produce 1 mole. So let's see if that actually is true. So let's calculate the first equation out. So we have 767.472 grams of HI. And so that is the amount of grams that is produced from hydrogen gas. So now let's do the same process for the iodine gas. So we have 2 moles of the iodine gas, and we're going to use the mole ratio as before. So for every 1 mole of iodine gas, there is 2 HI. So 1 mole of I2, 2 moles of HI. And so now that we're in moles of HI, we want to get to grams as well. So for every 1 mole of HI, there is the same molar mass that we used as before, 127.912 grams of HI. And so that will be the amount of grams that is produced from iodine. So let me write down what that is equal to. So that's equal to 511.648 grams of HI. So just to recap, for the 3 moles of hydrogen, there is 767-ish grams of HI. And then for 2 moles of iodine, there is 511 grams of HI. So we can see that the eliminating reactant here is the iodine, because a smaller amount of HI is produced from it. So that is actually what's going to be produced, because we need hydrogen and iodine gases. So what is actually produced is the 511 that we have here. So that's going to be our theoretical yield based on the amount of reactants that we have. So that's what theoretical yield is. So let me write that down. Theoretical yield will be equal to, and we started with 2 significant figures because it's 3.0, 2.0, and 1.0 values that we're given with. So that'll be 510 grams of HI. Ooh. Sorry about that. There we go. And so percent yield, what that means is that we have the actual yield on the top, and then the theoretical yield on the bottom, and then times 100 because it's in a percent. So our percent yield, I'll write that down again. So it's actual yield. So actually how much we make, and it gave us that in the beginning of the problem, and then theoretical yield, and then we just calculated for that, finding out which one is the limiting reactant, how much is actually produced. And so we have 1 mole that was produced. Actually, let's have it in terms of, just for simplicity's sake, so we started with iodine gas, right? And we know that this is the limiting reactant. So if we didn't convert it to the grams here, if we just look at this right here, just to moles. So the reason why I'm even discussing this is because it gave us our actual yield in moles. So it'll be easy for us to put our actual yield, or our theoretical yield, sorry, in also moles. So we need to have the same units. So before we converted this into grams of HI, this red box here, this is the conversion of moles to HI. So it's just finding the theoretical yield of moles and then the theoretical of grams using that next conversion right here. So before we used the conversion to get to grams, we had a conversion to get to moles. That's the first red box. So the 2 moles of iodine gas times 2 moles of HI, that'll give us, if we stopped there, then we would have 4 moles of HI produced. So 4 moles of HI is the same amount as the 510 grams of HI that we produced. It's just a different unit. I wanted to keep it in moles for calculating the percent yield because it gives us 1 mole of the HI produced actually. So we're going to put 4 moles because that is what is theoretically produced of HI. Yeah, I try to explain that in the cleanest way I could. But we just want to be consistent with our units that we're using because a percent yield doesn't have any units, it just has percent as the unit. So we're going to need moles and moles. Yeah, for sure. Yeah, so we have 1 mole of HI and we have 4 moles of HI on the bottom. And sorry, you times it by 100 to get a percent. And so 1 divided by 4 is 25 or 0.25, and then times 100, that'll give us 25%. So that is our percent yield. So that answers all of the questions that it was asked. Yeah, so we found the theoretical yield, and that's the 510 grams of hydrogen iodine, or hydrogen iodide, I believe that's how you say it, and then 25% yield. So those are all the questions that I have prepared for today. If any of you have another question, I can go over something more clearly or slower if anything is tripping you up. But yeah, hopefully this helped you with stoichiometry and limiting reactants and some of those conversions. So I will see you all next week at the same time, unless anything comes up. Yeah, for sure. Happy to help. Okay, then I will see you all next week.